Well, hello guys, here Mr. G with another video for the grade 12. This time we're going to be solving a question on electrostatic. It is question 8 from the mid-year diagnostic exam developed by Professor Rodriguez in 2023. This question says two identical conducting sphere Q1 and Q2 on isolating stands are placed with the centers 30 millimeters apart. When Q1 is brought into contact with Q2 and then moved back to its original position, Q1 gains 12.6 nanocoulomb of charge and it's negative, and the charge on each sphere is now negative 7.5 nanocoulomb. Very good question. Question 8.1 state Coulomb's law in words. So, what does Coulomb's law state? It states that the magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to the magnitude of the product of the charge. This one is important, it's the first very important part here. And inversely proportional to the square of the distance between them. If we write this one in symbol, we have that the electrostatic force is going to be directly proportional to the product of the charges, and the electrostatic force is inversely proportional to the square of the distance between them. This one is the same law but using symbols. You have to do it in words because the question said state in words. Now we are going to question 8.2. What is the magnitude and polarity of charge Q1 and Q2 before they touch? So now here we have the two charges and I want you to see the following here. In this question, they are giving us the change in charge for sphere 1. So this one we have here is the change in the charge of sphere 1, which is equal to minus 12.5 nanocoulombs. Now, if sphere 1 have that change in charge, it means that sphere 2, the change in sphere 2 will also be 12.5 nanocoulomb, but positive, guys, because remember when the spheres were in touch or touching each other, one of them gain electrons and the other one loses electrons. So if one of them the charge is negative, it means that the change in charge, it means that the other change in charge for the other sphere is going to be positive. Now they also tell us that at the end, which is the final charge, this one is the final charge for 1 and it's going to be the same for a final charge for 2. There is going to be negative 7.5 nanocoulomb. They ask us to calculate the initial charge for sphere 1 and they ask us to calculate the initial charge for sphere 2. This one is 1, that one is 2. That is what they ask us to calculate. And you need to remember that all changes is going to be equal to final minus initial. So we are going to do this and apply it for sphere 1 and for sphere 2. So here is all the data we have, which we just did right in the picture. So we're going to work for sphere 1. We're going to work for sphere 1 on this side and then later on for sphere 2. So change in charge 1 is equal to final charge 1 minus initial charge 1. Quite simple. When you substitute here for charge 1, we have that is minus 12.5 nanocoulombs equal to final, which is a minus 7.5, and then minus initial charge 1. When you rearrange this one here, guys, remember this one is moving to the other side, a positive here, you get the charge initial 1 is going to be equal to positive 5 nanocoulomb. Guys, this is simple calculation. You must try to do it so you can get the same answer. So if we go now for sphere 2, and for sphere 2 is exactly the same, just a different number. This one is the change in the charge of sphere 2 is final. Sphere 2, the charge of final sphere 2 minus the charge initial of sphere 2. And when you substitute here, you get that this one is 12.5 is equal to the final is minus 7.5 minus initial charge 2. And when you do this calculation, you get that the initial charge 2 is going to be equal to negative 20 nanocoulomb. Guys, once more, you can try it and do the calculation there. So we have here the calculation for the initial charge on sphere 1 as well as for sphere 2. It's a very good question. Didn't see something like this in a question paper yet. So here now in the picture we do have charge 1 and charge 2 before they touch each other. Calculate the magnitude of the electrostatic force that Q1 exerts on Q2 before they touch each other. So we're going to use the Coulomb's law formula to calculate the force between the two spheres. However, before we carry on, remember you cannot work in nanocoulomb, so you have to convert, and when you convert, this one will be equal to positive 5 times 10 to the minus 9 coulomb when you convert it, and in this case here will be equal to minus 20 times 10 to the minus 9 coulomb. That is how to convert to coulomb, because we have to work. The same happens with the distance. We cannot work in millimeters, guys. So when you convert here, you get that the distance, we're going to write r, is equal to 0.03 meters. Okay, and here we have all the data. I just want to show you before we answer that here in the formulas, that is the formula to calculate the force between charges, which is the Coulomb's law. So if we write the data, this data is the one that is coming from the picture. So I didn't do anything, I just extracted from there. And we write the formula. The force of the electrostatic force is equal to capital K multiplied by Q1, Q2 divided by the distance square. It's exactly the same. K is a constant also given to you in the table of constants. Here, you can see it here, so you don't have to memorize it. There is the constant, so please make sure you go there. And guys, you have everything, so the rest is just to substitute, and it's a straightforward calculation. So it's 9 times 10 to the 9 times the first charge, which is a 20 or 5, let's say it's 5 times 10 to the minus 9 times 20 times 10 to the minus 9 divided by the distance square, and the distance is 0.03, everything to the power 2. So guys, the rest here is just the calculation. And when you do that calculation, you get that the force is equal to 1 times 10 to the minus 3 Newton. Guys, make sure you recalculate this one and see if you get the same answer as I do. Okay? The next question is question 8.4 and said, draw the electric field pattern around both spheres after they have touched and return to the original position. Now, I want you to note that both charges at the end have a negative charge. Here it is. So both of them are negative charge. We're dealing here. We're going to solve that question right in this side here is 8.4. We have two spheres, and those two spheres are going to be negative, both of them. All right? So those are the two negative. They're going to repel each other. All right? And you need to know that the shape is going to look like this one. I don't like when learners draw too many lines. The more lines you draw, the more probability of making mistake. But all those lines are turned towards the back, except for the last one. So here is the shape of this. Remember, they are not going to touch each other. They must be in this specific way that they turn. And I draw the same number of lines. Okay, so be careful with this drawing. It could be a little bit tricky. Now, because they are negative, the direction of those lines is towards the charge. So this is how we represent the electric field around those two spheres here. It's very, very simple. Guys, this is the two negative charges sphere. If there were two positive charge, the shape will be the same, but the direction will be in the opposite direction or away. All right, question 8.5. An electron E is placed exactly midway between Q1 and Q2. After they have touched and returned to the original position, will the electron be accelerated or stay in equilibrium? Now, this electron, let's represent it quickly here. Now here you have Q1 and you have Q2. This is after they touch and after they've been separated. Both charges are negative, and you are going to place an electron which is also a negative charge. I'm going to draw a small sphere here. This one is an electron right in the center between those two charges. So what is going to happen? Because the distance is the same, those distances are the same. I'm going to say R1 is equal to R2. Why are they the same? Because the electron is right in the center. Alright, now charge 1 is going to be repelling that electron. This one here is the electron. Let's write electron here at the bottom. That one is the electron there. So charge 1 is going to be pushing the electron away to the right, like this one. This one here, I can call it force 1 on the electron, Alright, and then charge 2 is also going to push that electron away. So here, this other green one here is going to be force 2 on electron. Alright, now those two forces, guys, are equal because the magnitude of charge 1 is equal to magnitude of charge 2. The electron is common and the distance is common. So those two forces are the same, and therefore we say that the electron is at equilibrium. It's not going to move. So that is question 4.5. If we go to question 4.6, the electron is now removed. Calculate the net electric field at a point 10 millimeters to the right of Q2. Now, this question said that you are going to have, they want to know how strong is an electric field, is the electric field 10 millimeters from Q2 on the right side. And I want you to don't get confused. This one is not an electron. They want to know how strong is the electric field at a point which is going to be 10 millimeters on the right from Q2. So this one is 0,010 0.1 meters. Okay, now this point is a test point. This one is a positive charge. This one is not, have nothing to do with the electron. This is not the electron. They want to know at this point how strong is the net electric field. That is the question. Okay, so this is what they want you to calculate, the net electric field at point whatever this point is called. Now I want you to know the charges are going to be negative charges. Both of them are negative, you know that we did work. But this point, a test point charge, which is that point, is going to be positive. So what is going to happen here? Q2 is going to pull that point towards itself. So the electric field due to charge 2 is going to be this one here. And I want to move those numbers at the bottom there. So this one here is going to be the electric field due to charge 2. Remember, the point is positive, the charge is negative, so they are attracting each other. And the same is going to happen with charge 1. Charge 1 is pulling that point. Let's try to do that point a little bit there. This here is going to be the electric field. Also on that charge, on that point, is electric field 1. So you'll have to really listen what I'm saying so you don't get confused there. So you can see that both electric fields are pointing to the left. So both of them are in the same direction. So you need to know that the net electric field is going to be the addition of electric field 1 plus the electric field 2, and both of them are positive. If we say left is positive because both of them are pointing left. So all we have to do is to calculate separated electric field 1 and electric field 2. So we're going to start here with the electric field 1. Electric field 1 is due to charge 1, and this is equal to, let's show you the formulas. So be careful, don't get confused. The formula for electric field at a point is that one there. So this is the formula we're going to use for these calculations right now. So we come here and we say K multiplied by charge 1 divided by distance 1 squared. Alright, now we're going to substitute, even though we're going to speak about the distance right now. When we substitute, this 9 times 10 to the 9 multiplied by 7,5. Remember, both of them is 7,5, and I want you to note something. In this formula, you do not substitute the signs of the charges. Multiplied by 10 to the minus 9, everything divided by the distance. By the distance from charge 1, guys, is the distance which is the 0,3 plus the 10 millimeters. So this one is 0,03 plus 0,01, which is 0,04. That is the distance for charge 1. So it's 0,04 to the power 2. And you will get that the answer is 4,22 times 10 to the 4 Newton per Coulomb. That is the unit for electric field at that point, guys. Now we have to calculate the electric field due to the second charge. So we're going to go here, and it's almost the same number except for the distance 2 square. So you come 9 times 10 to the 9 times 7,5 times 10 to the minus 9. Remember, they have the same charge after they touch each other, guys. And here the distance is only going to be the 0,01 square. So when you calculate that one here, you will get that the electric field 2 is equal to 6,75 times 10 to the 5 Newton per Coulomb. Guys, those are the two electric field. All we have to do is to come here and substitute both numbers. We are going to do it right here. 4,22 times 10 to the 4 plus 6,75 times 10 to the 5. So the final answer is going to be 7,17 times 10 to the 5 Newton per Coulomb. Now Newton per Coulomb to the left. This one is the final answer with the direction, guys. And this is the end of this question. I hope to understand. It's a very good question for practice of the exams. Thank you for watching. Thumb up if you think it helped. Subscribe for the channel. I'll see you next time. Mr. G here.